Welcome to our review session for ME370 for the final exam. What are we going to cover today? Anything you want, but let's do a little spiel. This thing. These are problems I have put up on the Blackboard page. We can cover any of them. I think I've already posted the solutions. Well, some of the solutions, that's actually not a solution, that's just a spreadsheet. Some of these things, like I should have actually, this should be a log diagram, otherwise you wouldn't be able to get the numbers won't be correct. Look at how stupid that looks as a non-log diagram. We're not covering cumulative fatigue, so don't worry about it, but that's what it would look like if you were to do it. So here's some more combined stress problems. Stress element here. Yeah, I don't even know what we're doing in that one. Okay. Some fatigue. Shaft fatigue. We might do some shaft, it might have a shaft design problem as well, and we're not doing the cumulative fatigue problem there. There's also various problems listed, I think, on the Blackboard that tells you, hey, here's problems that you could try. Dr. Ghosh used to do this. Instead of giving homework, he used to say, here's suggested problems. And I think he gave the answers to them, and then he would just give quizzes and then exams instead of giving homework. I don't personally like that all that much, but these are problems out of the book that you should be able to do. Not necessarily in my, I try to write my own problems, and but these should be represented. Generally, these are too long, a lot of these problems. So we could try any of these that you want, or we'll go over homework problems, whatever you'd like to do. But these are representative problems. So if you have, I don't know where these came from. Huh. Oh, these are. I think these are actually out of Mechanics and Materials. Beer Johnson. So, anybody have requests? Let me see if I have that up on Blackboard. You can go ahead and ask. I don't. As I'm scratching this itch to see what exam prep. Yeah, so these are the review problems. So, any requests? We're taking requests. Anyone? You want me to just start riffing?
Can we start with like something simple, like as a warm-up, we can do like a stress element and just calculate the factor of safety. That'll be like, like a 10-minute problem.
Okay. Cool. Let's so just static?
Yeah.
All right. Without, we won't have to calculate the stress. It's like we already got the stress.
Yeah, sure.
All right, so let's pick out, let's see what are we dealing with right here? We're F23, ME370, final exam review. Didn't leave enough space. Stress element. Let's give him some tension and some compression maybe. And I don't know, let's pick out a material, a real material. You want to go SI or US? What do you think?
SI would be
SI? Okay. So it's out of A220. Boom. And, oh, we don't get enough love for the upper higher ones. Let's go 1095. So 1095 So we'll get a tensile strength of 830 and a yield strength of 460, so basically 460. So this is AISI 1095, and they didn't say this is hot rolled because they didn't have a cold drawn version of it, and I'll write down both of them, why not? My book's about to close. 830 megapascals. So let's aim for something high here. 460 megapascals. So, oh, I don't know. Let's go 350 megapascals here, and 250 in compression, and let's go crazy with this. Maybe 400 pascals. We can expect probably that we're going to exceed that right there. We could go ahead and do distortion energy theory right away, just right out of the gate, and we don't need to. We don't need to do more circle for this, right? So just remember that we could just use this equation. And so written it enough times to have it memorized, but let's look and see where it is. So it's kind of like unfair to just jump to it, but hopefully you feel that comfortable with it, that you could look at that thing and see, we have biaxial stress, but it's just in one plane, and we can use the von Mises formula that has all those in there. It could take a lot of extra time if you don't recall that, and you end up having to, I'm trying to find it. There you go, right. Yeah, it's kind of, sometimes some of these are hard to find. Why? Well, I know that it's right here. It should be right there. I am not finding that right away. There we go, okay. Equation 515, if you're looking for that right there. Equation 515 is what I've just written down. So some people might jump to this one up here, or then down to this one, right? This one you need all three principal stresses here. Of course, if you're only going to have two principal stresses, one's going to be 0. So this is the one to use if you already have the principal stresses. You'll note that this will look, if there was no shear, this would be the same equation right there, right? Because you'd have 0 for this right here. So all of these would be principal stresses. So it would be the same equation as this. So sticking some numbers in there. And so you go 350 minus 350 times negative 250 plus 250 squared. You could even put a negative inside there, but it doesn't matter, right, because it's squared. Plus 3 times 400 squared. And this is a calculator challenge. Oh, that should have been a square. I left out a square right there, sorry. 350 squared, 350 times 250. Boom. But now, because it's minus minus, we're actually going to add them together. Then 250 squared, add them. 400 squared, but times 3, and then add them, and then take the square root. And I got 526.6 megapascals. So if we had just the distortion energy theory safety factor, that's just yield divided by von Mises, or 460 divided by 526.6. F23.87, complying with my request for only 2 decimal places. I think it's logical because the 3rd decimal place, what does it do for you? You already failed. Why? Like the other day with the dead mouse, I made fun of the dead mouse. Why kick a mouse when it's down? Didn't seem fair. Wasn't nice. But it did make my wife laugh in the other room. I didn't know that she heard me. So yeah, I literally went ha ha to a dead mouse. You died. We could extend this and go maximum shear stress theory, and practice our more circle skills. Might even want to try to do it with be a little ambitious and try to see if I can figure out what a suitable scale would be to maximize this amount right here. That's a skill set. My machine design professor would really would take off points if this was. And I don't remember all the. It had sort of like a systematic way to choose the correct scale, so you could maximize the space onto something, so you could get the most out of it. But we did a lot more graphical things. There are still a lot of graphical things in here. But if you go if you look at this and say, oh, this is going to be the boundaries on the. You probably can't see it as well as I can, but these are like the big squares. Yeah, close to the big squares like this right here. So we want to try to fit it right in there. And the largest we have is like 525. So we could make these go 100, 200, 300, 400, 500. That would be a good one, right? Don Paquette might approve of that. I don't know. Dandy Don. Boy, people hated him. I got my first job because of him. Not really. The guy, my eventual boss, pulled my resume out of the pile because he saw the letter from Don Paquette. He wanted to meet the nerd who got that letter. Because he called me nerd to my face. That was nice of him. So let's see. We're gonna have 350. So 1, 2, 3. So like right in there, it's our 350 and 400. And let's see, the 400, we're going to do it for this face, right? Remember, when we're doing more circle, we plot a point for a face. So this is the tension side, and this is going counterclockwise for this side. So that's actually going to be the negative if we're going to be technically correct. There's going to be 400 down here. 1, 2, 3, right here. So that's where we would plot that point. And I don't have my ruler with me, so I'm going to have to do my best to draw a straight edge in my head here, or virtually. Okay, so here's 200. That's negative, right? No, 250. Need negative 250 up here. And then this is going to be the positive 400. So here you go, 1, 2, 3, 4. And so like right there. And we could also check where the center is going to be right away. So we go center is going to be the 350 plus negative 250 divided by 2. I should be able to do it in my head, but I'm not. I don't trust myself. I have trust issues with myself. That's going to be 50. So like right in there, and that looks about right. And here you go. I got my ruler. Well, that's not too bad right there. Look at that. And when it comes to an R for here, got to be careful. There's some people probably get used to a lot of times. This thing we've done uniaxial stress, and that point has been on this. So the R was a little bit easier to get. This one, I'm going to do it on this side because this one's straddling the thing, so it's going to make a little bit more sense to go for my R for right there. So R is going to be this value, which is 350, but we're going to subtract out the center. And so that's going to give this leg right here, if we stretch it up to right there, that's this leg right there is going to be 300. And then we're just going to have the vertical leg of 400 squared. So R should this be 3, 4, 5 triangle, right? But watch me as I do it, just because trust issues, I'll tell you. Oh, once you look at that, 500. And so, and then we can kind of try to sketch this out. Let's see. Well, first off, you know, we might as well see what the values are supposed to be and then plot them in. This is sort of like cheater-like. So we'll call it sigma A is going to be C plus R, or 500. Well, I should be 50 plus 500. If I write it like I just did it right there. So 550, and then MPA. BC minus R, so 50 minus 500, or minus 450 megapascals. So let's see, where's that going to go? 1, 2, 3, 4. So it's like right there. It's going to be sigma B. And then should be right here. Nope, right here. Right here. Sigma A. And then if I did this right, 500, right? It should be like right there. Or right there for my tau abs max. Oh, sorry. I'm a little wrong. It should be right there. And right there. Right. Not on the axis, but on right above the center point. Very intimidating to try to draw a circle in front of people. It's actually sometimes harder to draw the, let's see, I should have maybe made that a little bit. Okay, not bad. I'm going to give myself maybe a B plus on my circle. No, I don't know. Now looking at it, maybe it's more like a B, solid B. It's all right. I'll live with it. Solid B is good. We don't appreciate the solid B like we used to. People are all about like, oh, I got to get an A. I could do with an A minus. I'm okay with that. But a B, oh no, it's like I didn't. B's good. Just be happy about a B. So maximum shear stress theory. So what we really want to have is N maximum shear stress theory. We'll take yield strength divided by 2 over tau abs max, or 460 divided by 2 divided by 500. Is that true? Well, that doesn't feel right. Anybody feel wrong with that? It seems like a whole lot difference. 460 divided by 2. I can't believe that's true. That's so much smaller than this. So we must have done. Did we do something wrong?
I'm a little confused on how we determined 526.6 megapascals.
Excuse me?
I'm confused how we determined 526.6 megapascals. I was actually getting a different value.
Okay. What'd you get?
867.
Okay, cool. I must have done something wrong up here.
You got that as well.
You did? Okay. Thank you. well, kind of a good thing that I did both ways. 350 squared, 350 times 250, and then we added them together, right? We're going to add, then 250 squared, added them, and then 400 squared times 3, added them. Yeah, okay, sorry about that. 867.5, 867.5, and we should have got a much smaller number. 0.53. Thank you. And so now I can believe this one. They shouldn't have been that far off. 460 divided by 2 divided by 500. Yeah, okay, so 0.46. Still a pretty good ways away. And I'm just extending it. You said we'll do a short one. I said, okay, well, I did a short one with the von Mises, and now I've made the thing longer. We could also... Was that? We could, yeah. Let's extend that to there. First, I was going to do the maximum shear stress theory and von Mises on a stress yield envelope here. So the stress yield envelope, we had 460. Okay, that's fine. So we'll do the same thing here. So this is our extent right there. It's going to be 460. So that's somewhere like right in here, right in there. I went too far. Oops. The see-through ruler is so much better than this method, I'll tell you what. And if we want to do von Mises, we could even go a little crazy and sketch that in there. Oh, kind of went outside. Not doing great on that. I'm not proud of it. Okay, so what are our coordinates? Should be 550 and a negative 450, right? So 550 already, we're outside here. Here's 5, sorry, here's the x. But now we're going to have a negative 450, which is going to be like right in there. So here is about the point that we're dealing with, like right in there somewhere. That's our plot point. So we can kind of see these are the 2 points that are defined by how far away, where we cross the envelope. So kind of makes sense, right? That looks like about halfway in between this spot and that spot in terms of our safety factor. I went a little crazy with how large the stress was. Overshot that. But we could do brittle Coulomb more. We're unfortunate. Well, we had to do the conversion factor, right? Because I don't think it might be in this edition. My recollection, that is table A24. Yeah, table 824, and they don't have the they don't have this listed, at least in this edition. I'm not sure. There is the overseas edition. Anybody have that one? No. Okay. The overseas edition has these listed as might have them in conversion. And the conversion, I don't remember the conversion off the top of my head, so I will actually use the tables in here. I don't usually make you convert units, but if you had to, here would be the table where you would go to. Table A2. Good thing to it's a good thing to be very comfortable with units, or at least to be very careful. But now we have like online conversion things that you can, I use that like all the time. So I've lost a lot of my conversion unit memories. But anyway, we want to turn a pound per square inch into a megapascal if I can, but I'll take a kilopascal if I have to. So where are you at? Where is it up? No, wait. Oh, here you go. KSI into megapascal. 6.89. So you multiply by 6.89. So we'll go to table A24. Let's just pick out the largest one. Let's see if we can. Oh, I should have picked out the largest one to start with. Oh, okay, so I'm just fumbling right now, so excuse me as I get my head back on, my screw back on. So we're going to have 62.5 and 187. So I might go to the next page. Yeah, let's go to the next page. I'll go to the next page here. I feel like I have 2 pages. Do you ever feel like that and you're wrong? I thought I was right. All right, so this will be SUT of ASTM 60 has a tensile strength of 62.5 KSI and a compressive ultimate strength of 187.5 KSI. And then if you multiply it by the, I just lost it, was it 6 point something? What, 6.89? 6 point? Was it? I'll look again. Mr. Short Attention Span. .89. 6.89 megapascals per KSI. 6.89. So 6.89, 62.5. We get 430.6 megapascals and 187.5. Boom. We get a large 1,292 megapascals. So for the brittle Coulomb Moore, we go 1 over, and we go sigma A over SUT, and then there's the minus. But of course, that minus is just to counteract the compressive part of it. So 1 over, and sigma A was 550 over 430. Now, one thing to keep in mind, like we're doing apples to apples type of deal here. So this is already large, going to be, this is already going to be, we're going to have an overall safety factor less than 1. And so this is just going to make it worse. So there's the negative 450 here. And 1292. So I'm going to get the brittle Coulomb Moore is so I got 550 divided by 430.6 divided, and then 450 divided by 1292 add them together, and then take the inverse, so you get 0.62 for a Brillo Coulomb more. So if we decide, we want to use a something that's got more capacity, at least in the compressive. And if you were to plot this one out, you have to pick it a little bit more skewed. So let's say we're at right here, and right here. Actually, I don't know if I went far enough. So here is the 430, like right there, because that's 100, 200, no, did I do that? Yeah, 100, 200, 300, 400, so there's right there. 1, 2, 3, 4 right here. So we have these, something like that. But this is much more right here, right? So this is going to be 500. Okay, so that's not too bad. 500, 100, and so we're like almost 300. So like right in there. 100. No, there's 500, 1,000 right there. Yeah, 500, 1,000. I think I misspoke. And then like right into there. So I could just barely make it. And plotting these points, we have already 550 over here. This is the positive lead. You know, that's the sigma A and the sigma B, the positive. So we're already like right there, and we were negative 450. So we're somewhere like right there. So you can kind of see. But interestingly enough, if we wanted to do the modified more, we're going to be a lot better off with modified more. We didn't do modified more, but if you'll recall, that would like bring us down somewhere like right in there, and then down. Because the modified more is basically, you know, you treat the tension up to the tension limit up here in the compression, and then you start to do the diagonal. But this is more conservative and should match that 0.62 if you were to do the distance that goes from here to here. Or I'm saying this right here, that distance divided by that distance should get you the 0.62. Any requests? Yeah, it's a good idea. I like it. What type of fatigue problem? What kind of things? Combined stress? Do simple one first. Do simple one estimate the life of something? The trouble is, when you go on essay, you gotta like land right there. So we're gonna have to update as we go along to make it, you know, when you invent a fatigue problem. You don't know if you land in the right zone. Or let's we'll pick a we'll pick a, yeah, let's make a scenario. Let's just pick out a problem. Let's pick out a problem. There's a couple of them. There's some problems in here we haven't done. and the fatigue. It's been okay. So we're in here. Seems like there should be some more like that. I guess we'll just do one of these. Just do this. Let's do this problem right here. Problem 630. And I think that might be in the. I don't know. The figure shows the free body diagram of a connecting link portion having stress concentration at 3 sections. So I guess it's here, here, and there. Is that what I mean? I'm guessing. Okay. And the force fluctuates between 5 kips. I don't like kips, and 16 kips. Is this too complicated? Do you think? No, we're okay. All right. So let's do this one. I'll write the thing out, and we're going to use AISI Coldron 1018 and neglect the column action. Of course, it doesn't make any sense to neglect the column action. It's not a compression. That's stupid. That's stupid. And find the least safety factor if the material is this. I might want to pick another one of these. Force flux between 16 kips and 4. Oh, and compression. Recommend film here. No, okay, so there's not a one here that estimates the life. So we might go ahead and change this after we find it. They're looking for the safety factor. We're just going to do the Goodman onto this one right here. Okay, so let's take, this is our problem 613, 630, can't read, and it looks something like this. Making noises as it goes along. I did a terrible job of this. That's terrible. Should have used straight edge and used the lines. Wow. And this get recorded. Other people could probably see this. They can see what my ID number is too. Identity theft is real, Jim. From The Office, yeah. Do you ever see where he's got his actor friend, his Asian actor friend, to come in?
Yeah, I saw the little clip at the beginning where it was, I know the actor. I think he plays like the cop in Ant-Man.
I think he's in the new version of Quantum Leap too.
Yeah.
That was good. But the best one is when he Jim dresses up as Dwight.
Unreleased where they had like reenactment on the Matrix.
Huh? I don't know about. I know.
It's just on YouTube.
Oh, okay. All right. Bears beats Battlestar Galactica. Which bear is best? Well, there are two schools of thought. Black bears are best. They need to make more. My wife likes it so much she listens to the Office Ladies podcast.
Every week.
She almost falls off the treadmill. I mean, The Office has been off for a long time, and they're still doing it. I think the pandemic really made The Office even explode even larger because people needed a comfort food. So this is 3.5 inches wide and 3 inches there. And what else do we have? OD is equal to 0.4 inches and R is equal to 0.25 inches. All right, so we have two different spots that we have to check with this. And the force for this one at least fluctuates between 5 kips. Oh, here you go. 5,000 pounds. Let's say they call that force max, and force min is compression. There's some good things that we haven't covered in here that I kind of wish we had went over, but it's not. It's just things to point out. So maybe as we point them out, it'll be useful to us. Okay. So, and then we also have AISI 1018 cauldron. All right, so we got some things that we can take care of right away. Let's go get we will get the material properties. We need the ultimate strength. We can do that. So I usually when I write the exam and time it, and then I'll start removing stuff, and almost inevitably I remove you looking up the material properties because that's like an easy one. Sometimes for certain things I'll give you the cross-sectional properties because that'll reduce it some. But other times I'm like, well, that, looking these up might be the thing I want to see. Do you recognize what you need to do? I don't know. It depends. So this is going to be 64 if I've been paying attention for my 1018. 64. We can also get the 54, but I don't think we're going to use it for anything. It was 64 KSI, and the yield is 50. Did I say 54? KSI. All right. And so, like, if we're making, sometimes I will ask you to go through the process of finding the endurance strength. I won't ask it multiple times, but at least just once. You want to try to get that kind of thing. Makes you pay attention, but don't you want to be able to do it quickly. Let's go get the stress concentrations first. So we'll look these up. We could do it ahead of time, but let's go ahead and look for it and then decide what factors we need. All right, so we need a D over W factor for the whole. Let's do that one and look at the area, right? We want to make sure that we're using the thing in the caption here, right? It's not crazy, this is not a difficult one to like figure out on your own, but sometimes there are some weird stress concentration things that require you to use that stress or convention for the stress. All right, so this is for the whole. And we're going to end up with, we want a D over W, which in this case, that's going to be 0.4 over the width here, W1, or 3.5. So they're pretty close to each other. So 0.4, 3.5, we end up with 0.114. That's good enough. 0.114 on here, that's not easily done. This is obviously 0.1 and 0.2, so we're going to hug close to here. I would say this right here is like 0.13. That looks like about one, well, a little bit, that's actually pretty close to 1/2. So it might be, yeah. So that's like 0.14. So we're talking about like somewhere up in here, which means these are always crazy right here. Like I would say that right there is 2.7. So 2.65 or a little bit higher than 2.65. Let's go 2.7. No, that's that 2.7. Let's just go with 2.65. Are you going to go crazy on the exam? No, I don't think so. So KT approximately 2.65. Well, let's so the area for this one All right, because all these stressors can be F over A. So the area for this one is going to be, they call it W minus D times T. And I forgot to do the H up here, up above from the original problem. I didn't write it down. So that's just typical. What a time waster. What a waster of time. And H was 0.5. No, I'll write it over here as if I did it all along. So this is going to be 3.5 minus 0.4 times 0.5. I could do that in my head. 3.1. 3.1. 1.55. 0 inches squared. All right, so we could do the other one is going to be off of this figure. We need big D over little d, and we need R over little d. So you go, this is the fillet. I got the hole there, fillet. Don't call it fillet. They'll make fun of you. And for us, that's going to be big W1 over W2, which is going to be 3.5 over 3 1.167. And we need R over D, R over W. Oh no, it's going to be the smaller of the two. And they said that R was 0.25. Look there. And we're going to divide by 3. What's that?
It's like 112. Yeah.
Oh, yeah. Oh, 112. I got you. Okay. I was thinking 0.12. No, I got you. Yeah, 0.8333. All right. So this is also a challenge. You know, it's a concentration challenge almost more than anything else. All right. So we had. Let me look at it again. 1.16. That's close to 1.1. All right. So we're gonna hug the 1.1, and then we had the 0.08. So here's 0.075. Right. So a little bit above this and a little bit to the right. Yeah, it's looking like 1.8's not a bad choice. Everybody okay with that? All right. Because we're going to look it up in the book and find out how far off we were. I don't know how intimidated you are by that. I know I am. Just a little bit. I don't want to be a dummy. Take my birthday away. Oh, yeah. I only heard one person one time say that at the academy. I always love that. What can they do? Take your birthday away? Like, what? That's a terrible thing. Look how sad it would be. Someone take your birthday away. So A is going to be, for this, is going to be, what did they write? DT or W1 times T or 3 times 0.5. I could do this 1.5. Got it. It's the little, yeah, thank you, man. It's the little thing you're going to get like, oh, that just, I'm so happy by that. What are we doing next? Okay. We could find out, we want to probably convert this stress concentration into a fatigue stress concentration. Something we can get out of the way. There's no order that you have to do any of these things in, but maybe just think of it as looking for incremental little things where you go, I got that done. I got that. It's a good way to think of life, just to get through the day. Just flip, 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 flip. These are relatively long problems. Huh? This is the one we want, and we had the ultimate strength of 64, so it's close to the 60. All right, and our notch radius, well, at least the notch radius for, there can really be two separate ones. No, they're the same, right? Because you have the, no, that's not true. The diameter is 0.4, so it's got a radius of 0.2. So we might want to stick that back up in there. I don't know. I didn't do a good job of separating this thing out. So the Q is approximately, so 0.4, so it's close to this, 0.2. Wow. No, I'm going the wrong side. My bad. Point is not even on here. Well, what's good for us is it plateaus, gets flatter. So what you do is you look up and you go, there's something like this right there. Or you go get the equation. No. I can't quite see because my eyes are bad. But damn, that's close to 0.8. Right? Because it's just a little bit above this. And it's right over there. And it looks like it's coming there. I'm going to go 0.8. Is that okay? Sure. So for that one, 0.8. You know, and I can always just say, I use the little squiggle thing. So the other, we got the same. We got a radius of 0.25. That too is not on there. So they also get a squiggle, 0.8. We'll see what the book says later. Solution. So we have, okay, so for, I need to rewrite this out. For the whole, KF is
What table number is Q again?
it's in table 626.
Thank you.
You're welcome. Or figure, yeah. I'm not trying to correct you. I'm just.
Graph.
Figure, table, doesn't matter. Except I do have a little pet peeve about when labeling stuff in reports. Remember, I put the table gets labeled on the top. The figure goes on the bottom. Tabletop. That's how you remember. Just good to know. So 1 plus 0.8 times our first one was 2.65 minus 1. Is it going to fit in there? Sure. 2.65, subtract 1.8, multiply, add 1 back. Boom. 2.32. And the fillet, not a fillet. Same dealio. And now we got the 1.8 though. Why did I put that? I don't know. Doesn't matter. 1.8. I could just write 0.8, dummy. Okay. 0.8 times 0.8. I bet it's 0.64. It is, and add 1 to it. 1.64. Could have done your head. Could have. Didn't. Could have, didn't. All right, so here's an option that you always have, right? Because we want to have alternating and mid-range. We could actually find the alternating and mid-range forces and then find what the alternating mid-range stress is. Or we could find what the minimum stress and the maximum stress are and then find the alternating and mid-range. Either or, doesn't matter. So let's go ahead. It'd probably be a little faster, only slightly faster, if you find the alternating and mid-range forces. So here you go, max minus F min. This is the you do the absolute one for this one. And then the mid-range force, and you go F max plus F min over 2. This does not have. This one, got to be careful. This one is not the absolute value. This one is the absolute value. We don't care whether this one's negative, but we do care about the mid-range being negative. I'll explain about that here in a minute. It kind of messes up this problem. I think it messes up this problem, but we'll see. So what was the maximum was 5,000, and the minimum was a, whoops, I forgot to put it, that's compression. I didn't label it up here above, so I'm going to leave it up. There's compression, and this is tension. So that's why they told us about the, forget about the column buckling. Bless you. But this one didn't matter right here anyway, so we ended up with, I can't do the math, 21. So it's what, 10,500 pounds. I don't like kips. Here's the one that it's going to give us a little bit of problems. This ends up being a negative, right? And we have 11 divided by 2. So 5,500 pounds. So now for the whole, what we're going to find is the alternating is going to be KF times FA over A. Did I get that right? And this is going to be 2.32 times 10,500 over 1.55. And of course, we're going to turn it into KSI anyway. So, all right, so 10.5 times and then 1.555. All right, so we have 15.72 KSI. The mid-range (2.32) negative 500 right there over. Yeah, and this is a sort of a pain in the ass, this one. All right, but that's right. We haven't dealt with what the consequences of this yet. So that's 8.232 KSI compression. So we might consider changing what those loads are. So we're actually probably pretty good, everything up above here. It's when we got down to putting these in here to be able to make the problem be a little bit more interesting and do things. But we'll see this other one there. We go, let's just write the thing out. That's going to be 1.64, and we just have this is just slightly different denominator, 1.5. We should really just use the life of the thing. Like, we already know that the fillet's not going to be as bad as the whole. I think that's true. Yeah. I can't think of a reason why it wouldn't be. It's got a lower safety factor. I mean, a lower stress concentration factor. So 11.48 KSI tension, and mid-range 1.64, negative 5.5, 1.5. 1.64. And so you get like a 6.013 KSI compression. All right. So, what are we doing on time? We got ourselves set up for here. Let's do the tedious material. Where we're going to go SE is equal to KA, KB, KC, KD, and KE. SE prime. The SE prime is just 0.5 times ultimate, or 0.5 times 64. Math, 32. Woohoo! KA, this is, let's use this 11th edition for this information here. I can't decide which way is it. It goes this way. All right, so here's the equation we just used right here. And then we're cold drawn, so we're going to use a 2 for our coefficient and an exponent of negative 0.217. And that's applied to this equation. Ka equals A S ut to the B. So 2.0064 raised to the negative 0.217. And if you get a stupid number, double check what you did. All right, here's one. Okay, so this is KB. Got to pay attention to this. This is the size factor, but you got to read closely. Or remember, don't just jump to the thing. You make sure we were looking at here for axial loading. There is no effect on size. So KB equals 1. Yay for not having to do things. So drum. KC and the Sunshine Band. Make a little kick down tonight. 0.85. Problem didn't say anything about the temperature. Problem didn't say anything about reliability. Therefore, we can get our SE 0.8111, 1.85, 1, 1. Whoop. I forgot something. Hello. 32. And so we get 22.06 KSI. And let's just pretend that we might have some desire to find life. So let's go back a couple pages and find out what A and B are going to be equal to. So first off, to get A and B, for our SN diagram, we find this. Now we gotta go, oh, wait a minute, our ultimate strength is below 70. What do? We're at 64. When we look for a little note, I want to look for a little note. It's got a little note here. It says, determining here. Where is this? Okay, there it is right there. For values of SUT lower than a limit given, F is equal to 0.9 is recommended. So F .9. And so the equations here for the coefficient, so we're going to use, we're doing this, so for the equation here, find out the number of cycles. So N is equal to rev over A to the 1 over B, right? So that's the relevance of the thing. That's why I'm writing it right there. Where A is equal to this is equation 613. FSUT squared over SE. Let me write out what this. Okay, so a lot of times it's just a little convenient to write these two together. 0.9 times 64 0.964 times, so that's 57.6 KSI. So we will say that's 57.6 squared divided by 22.06. So it's 150.4. And that was still KSI, by the way, if you were to care. And then we also want to have B is equal to negative 1/3 log of FSUT divided by SE. All right, so that's this guy up here, equation 614. And so B is equal to negative 1/3 log of 57.60 divided by 22.06. And make sure that you know it's negative. All right, so 57, well, I already had it in my calculator, and for whatever reason, forgot 0.06 divided. And to take the full log, not full log, the log base 10. And they go 3 divided, so we have negative 0.1389. You'll need it later on. Okay, so let's go modified Goodman on this. So N good is going to be equal to 1 over alternating divided by SE. And then go plus mid-range divided by ultimate. Is that true? No, it is not, unfortunately. This is one of those things where you have to be careful not to blindly follow an equation, but apply knowledge. What causes fatigue? Crack. A crack opening and closing. If there's compression, it will not open and close. So, and this can be witnessed by one of the first figures in the fluctuating stress thingy. Technical term. Where you at? There you go. Boom. All right, so on the x-axis right here, we have the mean, right? The mid-range, if you will, mid-range stress. Over here on the right-hand side, if it's tension, it matters. Over here on the left-hand side, it doesn't matter. Whatever you have as a compression doesn't matter. So for this, if it's compression, it's no bueno, doesn't matter. So all you really end up having is 1 over sigma A over sigma SE, which is the same thing that you would get if you have a regular safety factor, right? So, and good. That's why I was mentioning, like, you heard me before hemming and hawing over the nature of the problem, like, and we haven't covered that. I didn't emphasize. We were going to, when it came to doing the raindrop analysis thing that I described, because it's like a check that you need to make as you're looking through these different cycles that's going through. If it's mid-range was negative, you just ignore the mid-range. But anyway, so in here we're going to have our 22.06 divided by the alternating, which we decided, well, the worst alternating that we have is for the whole, right? And we're describing the life of the thing, so we're going to get 15.72. So we're going to get a safety factor that's going to be greater than 1, and what does that mean? It's going to live forever. And how much is going to, how much of a margin? We got like a little bit of a, like 40, a 0.4 margin maybe of it living forever. Safety factor. Of course, safety factors are all about covering uncertainties, right? So we don't know for certain, but we have like a little bit higher confidence, but not much. And if it's a critical component, we might have some rule that we have to have a safety factor a certain amount. So this might not be satisfactory, but if it's just as we have this, remember we also have, we also have, didn't have anything mentioned about reliability. So right now, this is a safety factor 1.4 with 50% reliability. That might not be good enough for us. So it's not going to tear it tremendously down until we start to get up into really high amounts for reliability onto the thing. So that's the some of the there's like a difference between certainty and reliability, right? The certainty is like, well, we're trying to have a factor that covers that certainty, and related to it is if you want more reliability to improve your certainty. Right here, we would take a reliability factor and reduce it down, right? But that 0.702, what you end up is you'd multiply it by this right here, and you'd knock the thing down considerably, right? So what if we go 0.702 times thing? Now we have 0.985, right? So if we wanted to be 99.99% reliability, then we say, okay, yeah, the thing is going to die. But not enough for me right now because I wanted to go ahead and find out, predict the life of the thing. But now on an SN diagram, as we would have, it's going, I want you to get used to the SN diagram. We're going to have, right here, this thing is going to be down here. It's underneath. Right, so you can't. It doesn't intersect anywhere in between the 1,000 right here. We need to have higher to be able to have do the stuff that we usually do. So I know this was a longer problem. We wanted to do a short, quick introduction problem, but does it make sense, everything that we did? Yeah. It's covering a lot of ground, but it's...
It won't be a problem this long of the exam, though.
No, I try not to, but I've also was talking the entire time. I think you could probably just practice and get a lot faster than what I did right there. I also did for 2 different loads, for 2 different, you know, not 2 different loads, but 2 different positions onto the thing. But let's continue on with that problem because I want to, we don't need to start a fresh problem. We could just use different loads to be able to do the next portion of it, which is the modified Goodman and then finding, predicting the life. We already have everything we need for that, so we'll continue. And let's just check and see what we did things correctly right in here. So I will go into space. I wonder what's on my computer. So I hope it's nothing. I think it's fair. I think we're okay. I don't know. There. Oh, hide the volume thing. That's what I had right in there. I also was learning how to set up Microsoft Teams. So far, I don't like it. It's actually. But old man complained. I was talking with some friends on the internet, and I guess we're all old men. We're reminiscing about computer programs that we used to like that are gone now. That's a pretty old man thing to do, isn't it? Shigley, we're 11th edition. I don't know why they have them in Word, but they do. This is 630. Let's see. Now I'm showing people on the internet too. Where'd you go, man? Hello? Are you just taking your sweet time opening it up? Are you just going to tell me to help? All right, I'll just go scroll down then. Oh. I'm not doing anything, apparently. Oh, there you go. Tell me to open it multiple copies. Word hates me. My computer hates me. So I hate you too. So I hate is such great. I know. Not hate. Hate's wrong. All right, so we get 22. That's good. That's good news. Ooh, 6.31. Why? I don't know. Why did I get that?
That's another higher paper. I got 2.5.
Oh yeah, their stress concentration is 1.72. What did ours have? Well, they have Q is 0.85. Yeah, you just said that, didn't you? I'm sorry. Oh, where's the other? Oh, that's for the. Okay, yeah, right here you go. Since the mean stress is negative, so they got 1.83, and what did we say we got? We got 1.83. Wow, that's so much higher than ours. Well, their alternating is 12. Why is our alternating so much larger? 15.57. Maybe they're talking about the hole. Well, that's for the fillet. Okay, here's the hole. Okay. So they did them separately. And they got 1.33. 1.4. I can live with that. Here's what I want to know about the next one. Okay, good. All right, so with that loading, so let's use that loading. We can come back and use this one again. So, all right, so they're loading in the next problem, 631. Maybe it's this room. You guys aren't giving me the energy you want, man. You're not like having fun. No.
Why the desks?
It's the desks. They're terrible.
I hate these desks.
I've complained so many times.
I think throwing things off of these desks, like so many times.
You know, I used to.
Whatever design is, serves
I used to.
all of the first things in life.
I used to allow the electronic version of the textbook in this room and so many, I heard laptops like falling like all the time, like falling and landing. I'm like, all right, we're just gonna get a hard copy of the book. Especially since it's like $20 if you get the 4-in-1. I'm just no more laptops falling on the floor. But
The coffee cup off one of these ones. By accident.
you know, you know, and then we're gonna have some seriously full classes next semester. They're talking about like getting rid of one of the sections from dynamics and make them 24 each, 24 people, and they have you can't get 24 people. They're gonna have to get another classroom. And 308 like right over there.
They're putting in that 308 over there.
Well, they have a capacity of 20 or something like 22 supposedly. You can't get 22 people.
Oh, man.
Do they pay based on like how many classes or how many sections you teach?
No.
Or-
Well, I mean, you can get if you want, you can get an overload, but it's only what basically what the adjuncts make, and it's
Well, I don't
not
know.
much money at all.
Like you got paid based on your 3, and they were trying to cut your pay by mushing you down to 2, or I didn't know how that worked.
No, you're guaranteed a salary onto the thing, but it's I don't know. It is what it is, I guess. Anybody that there's complaining that takes place, but what are you gonna? Is that gonna make it any better? Ooh, wait a minute. Let's see. I don't like this next one here. Instead, they made the size. That's gonna make me cause more problems here. They changed the size to the width of being one. Yeah, I have to read you the whole frickin' thing then. So we're going to change it by, hopefully we'll pick some better numbers right here. We're going to go that it's going to be, what would happen if they were both tension? They went between tension and tension. I think we're going to have a higher thing. All right. So I think we're going to be enough. I don't know. Well, I'm going to take a gamble. I'll pre-apologize if I get it wrong. So it's not 631. Hopefully this causes the stress to go higher. We'll go the alternating. So F max is now 1,600 pounds tension, and min is 5,000. Go for the 5,000. Only because I don't have enough creativity. So you have the alternating now is going to be 16. Well, I don't like this. Yeah. Anyway. I think it'll be enough. I think we'll be okay.
This is the gamble part, right?
This is the gamble part. This is the part I don't like. Well, we're going to try it anyway. I just thought about what it's going to look like, right? So all of a sudden, we're going to be on this diagram. We're going to be over this way and down low right there, and that's probably not going to do the thing. We want to get it up higher. So we want the alternating. See, because my alternating was 5,500, and now it's going to be. Well, my mid-range was, so now the alternating is going to be, so I wish I had done this ahead of time, sorry. Let's make this 25,000. It's probably going to be way crazy high now, but let's see if we can do it. All right. So I'm going to do 25,000. Divided by 2, and so that's going to be 5. It's going to be 10,000, right? Pounds, and then we'll have the mid-range is now going to be 25,000 plus 5,000 over 2, and so that'd be 15,000. Is that right? I still don't like it. Yeah, because 30 divided, yeah, so 15,000. So let's just go for only for the whole. is we already established that the fillet isn't going to be nearly as much, so we're going to have the alternating is going to be 2.32 times, I'm still messing the thing up, because that still isn't high enough. All right, let's see what happens. Like I said, I was going to pre-apologize, which Lori says this doesn't count. You can't just negate the terrible thing you're about to do if you apologize for it ahead of time. So it doesn't make it better. Then just don't do it. Yeah, well, this the whole point of the pre-apology is no. But here's the thing: I've got the new thing is credit for things I don't do. I said, or credit for things I don't say. But here I get to say them though, right? Because I'm like, you know, I was going to say something that was really bad. And she goes, "Go ahead and say it." So I say the terrible thing, and she goes, "Credit for things you don't say." So it's right there in the pre-apology. Yeah. I tell you what, I could give lessons on how to be married. I'm like, that's how good I am at it. Be just like me. No, don't be just like me. So we have our 22.45 KSI. All right, let's see. Can we get a Goodman to be below? So we go our, remember, sigma A over SE plus sigma M over SUT. Fingers crossed that we broke this son of a gun. 14.97. See, there's a good amount right there out of our, where'd we go? Where'd you go, buddy? 22.06 plus, now we have 22.45 divided by 64. I didn't put all my hugs in there. Did I ever mention that's what I think of the parentheses are hugs? Nice and cuddle, cozy. But sometimes the numbers run into the other numbers. You can't tell that number's. I'm giving them all a little space. A little. I shouldn't say things out loud that are in my head. Just keep them there in your head, Ted. Ooh, look at that. Rhymed. 22.06 divided plus. Boom! Barely. 0.97. All right, but it counts. It counts. Now, we killed it. It's going to die. Let's figure out how long it's going to live. It's going to be nearly 1 million, right? It's going to be very close to 1 million. Let's hope. That's how numbers work. Let's see how numbers work. Now what do? We have to figure out a single value of reversible stress that encapsulates these two together. Truth be told, you can almost add them together, but we're not gonna. So we use the equation. It's different in the different versions. One of them calls sigma rev, and the other calls it sigma something I can't remember, but I'm about to look it up so we can go ahead and see what it's called. Flip, 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 flip. This is the sound of flipping pages. There it is, right there. All right, so they call it a, what the hell is that thing to say? AR? Yeah, sigma AR. So in one of the books, in the 12th edition, the sigma AR is called sigma rev, and this equation is inside example 612. So if you have the 10th, 9th, 8th, and so forth, you don't have this equation right here. It's equation 658. It's actually inside. And so because there are people who have the other one, let's take a brief moment to point it out. So where did that guy go? Where did my... be somewhere in here. This is boom, boom. Oh no, no, it's right here. It's in this. Shigley? Yeah, there you go. Alright, so in the 10th edition, it's in failure, it's in 6, it's combination loading, there's right there, that's right there. So, there it is, okay. I'll get you out of the way. So it is located in 612, it's right there. Here's the location of that same equation. It's not any other place. What they're describing, once again, this is a graphical sort of approach to plot a spot on the alternating and mid-range stress diagram, and then plot a point through there, and then a line that's starting from the ultimate strength and passing through that line and intersecting with the y-axis, and that's defining a new stress like there. So it's easier to describe or show it. Let's get the equation down first, and then I'll put a little graph onto the thing. So I still think of it as rev, because what we're finding is the equivalent completely reverse stress. And it's the alternating divided by 1 minus the mid-range divided by the ultimate. And it's not going to be that much, I don't think, different. Well, we'll see. That's going to be 14.97 divided by 1 minus mid-range of 22.45 divided by 64. And so 22.45, 64 divided, 1 minus, change the sign, 14.95, and boom. So we end up with 23.03 KSI. What that's done for us on an ultimate strength here and an endurance strength here, here was our Goodman. You know, this is the alternating and this is the mid-range. What we've done is let's see, our alternating, I'm looking for, oh, I should look right here. Alternating is like 15, so it's somewhere like right down in there, but it's really damn close. I mean, it's really damn close, right? I should make it really damn close, right? Because it's just outside the envelope. It being at 0.97 means that it's just outside the envelope, so it's not that upper dot, it's that lower dot, right? So and we could even, here's our load line. This is the graphical way of describing. You could see, right here, it would be this line divided by that line. That distance is what the safety factor is right here. So what we've just done, this rev right here, is we've taken a line and we've started right here at ultimate and have a new line designated through there, and this is going to be the sigma rev. Does that make sense? Like the kind of the mindset? We're trying to find an equivalent. So this dot right here is a combination of, here's our alternating. It's kind of weird to have that two different labels of the same thing right here. Let's call this alternating. And here, let's call this mean or mid-range. I think mid-range is better. Right. So here's the point that we plotted out for our stress condition. And this was Goodman's line, and we're outside the safe envelope. So we're going to go, okay, well, how do we find an equivalent alternating? Well, let's take here and we'll go project it right through that and find that's where we would go. So with that, we would say, okay, well, let's predict the life based on this. We'd say, okay, predict life. And we'd have n is equal to 23.03 and divide it by 150.4, oops, and raise it to the 1 over negative 0.1389. And we're going to, it's going to be a little bit less than a million, because a million's what the whole graph is based on. If we're right, I don't know. And I go 0.1389. I'm a little nervous about this one, but let's see. Yeah, 737,080 cycles. But 740,000 cycles is a better answer. I'd even say, give me 700,000 or 800,000, because I'm not buying that it's going to live 740,000 cycles. It's got all kinds of variables in there. But if we come back to this right here, we'll see that this was SE. This is F times SUT. This is SUT. This right here is 1,000. This here is 1 million, or 10 to the 6. I should probably do a 10 to the 3 right here. And we are just above. Here's our sigma rev, and we're going to come down to here, and that's what we're predicting is going to be our n. Does that make sense? I made it to a long problem. I just took Sai's exam for Thermo 1, his final exam. I had to send it to him and ask him, what the hell is that?
I think that's what his thermal 1 exam. What's his thermal 2 exam right now?
I don't know.
Congrats, too.
I don't know. You're going to do great. Positive attitude, power of positive thinking.
I think I'm going to be good next year.
So that's the opposite of positive thinking. The positive thinking.
He's going to have to curve like 60 points.
Yeah, but you have one of those guys made like 100 in your class. 100. So the curve breaker. That's the kind of guy that you got to give a blanket party to if you're in the military.
He missed like 28 quizzes already being out. So that brings his grade back down. So that allows a curve in the final grade. So that's
There you go. There you can hope. That's where you missed your bright side in it. That's good. What do you want to do? What do you want to do? Want to call it? Want to go? Want some more? I'm ready. I'm ready to go. I'm ready to go.
Having to be covered.
There's some combined stress things. You're still going to ask a combined stress problem. I know. Pressure vessel problem. Still probably have some pressure vessel in there. And you're like, it's not like I want to beat you up over it. Some people have done it well each time. Some people have yet to do it well. So I want people to, exams aren't punishment. They're a measure of your progress, measure of your mastery. Grades aren't gifts. They're not mean. They're not punishment. They're just a measurement. Got to measure.